Is your Stat 100 lecture, Coronavirus Edition. I am Edward Doolittle. Today's lecture we are going to start Chapter 8. So I'm just going to first talk about the first few sections of Chapter 8, which are sort of general commentary. And then later on, we will get into specifics of large sample estimation, which is the topic of this chapter, and we will solve some actual problems. So I'll divide it up by textbook section. So I'll be doing sections 8.1 through 8.3 in this lecture, which is a fairly general discussion, and then I'll be moving into more specifics in another video. I created this video with my iPad and my Apple Pencil using a program called Notability and a screen capture on the iPad. I believe this will work. If it doesn't, though, I guess I'll have to go back to the drawing board, as they say, and try some different software. But I'm pretty confident this will work. I've tried it a couple of times before for my other course. So let's go. The subject of this chapter, Chapter 8, is large sample estimation. And these two phrases both mean something. Large sample means our sample sizes are at least 30. Sample size is the number of individuals in the sample, and it's at least 30. We've talked about this before. Large sample always means sample size is bigger than or equal to 30. Estimation is something we haven't talked much about before, but this is what we're going to be talking about all in this chapter. I have mentioned before that there are some important numbers that we might want to learn about in statistics. Those are things like the population mean. That's the population mean. There is the population standard deviation. And there's also the population proportion of successes. These are all numbers that are associated with the population. So these are called parameters, and we have used this term, I think, as early as Chapter 1 of this textbook. These are parameters. And as I've mentioned many times before, parameters are generally difficult to impossible to determine exactly. So the population proportion of those who are going to vote Liberal in the next election, we can actually find that out. We hold the election. It costs whatever it is, $100 million. And most researchers don't have access to that kind of money. Same, if we want to determine any of these parameters, we have to survey an entire population. So that can be very expensive, or it can be impossible in the case of hypothetical populations, which, when I say women smoke less than men, I'm talking kind of hypothetically about all women versus all men, and I can't possibly survey all women because there are women who haven't been born yet, for example. So I generally cannot determine these population parameters exactly. So what I am going to do is to try to estimate those population parameters. And that is exactly what inferential statistics allows us to do. Inferential statistics allows us to infer information about parameters. Given only information, a large, in this case, information about a large sample. So that is the miracle of statistics, that we can say something about these numbers, mu, sigma, and p, given just information about a relatively small sample. The exact sample size will depend on the needs that we have. We will get into a discussion about how to determine a good sample size later. But for now, we know we need at least 30. Sometimes we'll go up to 1,000. And somewhere in that range will be our population sizes, and that is, quite doable given budgets that we might have for research or for surveys or whatever. All right, so we have these three numbers that we're interested in. In particular, in this chapter, we are going to focus on these two, mu and p. Sigma, we are not going to spend a lot of time on, maybe just a little bit, but not very much. This sigma, estimating sigma, is the subject of later on in the textbook that we're not even going to cover in this course. So really, we're just going to concentrate on mu and p. All right, so those are the parameters that we're going to try to determine. Now we have here different kinds of inferential statistics. Different kinds of inferential statistics that we can talk about. In this section, we are just talking about estimation. And just to give you a very quick preview, the next chapter of the textbook is about hypothesis testing. The mechanism that we're going to use for estimation is something called confidence intervals. And I use the abbreviation CI for confidence intervals, and hypothesis testing has the abbreviation HT. And so that explains some of the words that we saw in the course outline at the beginning of the course. In the course description, if you look in the calendar, you'll find that a lot of the stuff in the calendar is about confidence intervals and hypothesis testing. So we now know what those words mean, and this represents progress in our learning, I suppose. All right, so for this chapter, we're just going to concentrate mainly on estimation. So there are a little more vocabulary that we need to pick up with this. So an estimator is a rule or a process, usually expressed as a formula, that tells us how to calculate an estimate given a sample. So an estimator takes a sample and gives us the rules to provide an estimate from that. And there are a variety of different kinds of estimators. So we're really going to be talking about two, and the second one is the most important. One kind of estimator is a point estimator. and that is what do I think is the best value, the most likely value for mu or for p. Those are point estimators. And we generally don't like point estimators because they are misleading. So you may find them in popular press, in newspapers like USA Today or something like that. You'll find lots of point estimators. And people get used to using point estimators, but they are rather misleading. They're quite misleading. And so what we're going to spend most of our time on is interval estimators. Interval estimators are the way we must go. So we're just talking about point estimators just to talk about something that's bad and something that you shouldn't do. And there is a relationship, though, between point estimators and interval estimators. So I guess, it's something that we do need to talk about. It's just something that we shouldn't stop at point estimators. We need to go on to talk about interval estimators. So a point estimator is my best estimate of what the mu might be. And here's an example of a point estimator. So a point estimator for mu is x bar. Oops, that didn't come up very nice there. I'm going to erase that. Point estimator for mu is x bar. So what this says is that I find my sample. I take the sample mean. So whatever number I'm measuring, I record that, and I take the average of the sample mean. I get x bar. I'm going to say that is my estimate for mu. So that is an example of a point estimator. An example of a point estimator for p is p hat. P hat is x over n. And if you remember, in the discrete context, this is discrete and this here is continuous. In the discrete context, x is the number of successes, n is the total sample size, and so x over n is the proportion of successes in the sample. So p hat is the sample proportion of successes. So p hat is an estimator for p. So we don't know p. We're trying to figure out what we can about p. And if you said, I need one number, and I don't want to hear anything else, I just want the one number, then the number that I would give you is p hat to estimate p. And the same thing, if you want to know something about mu, and you're very statistically naive, but you just want one number, then the number that I would give you is x bar. So those are point estimators for mu and for p. Now, what's wrong with this? Well, the textbook gives a nice example. I kind of like this example. They talk about shooting a bullseye. So imagine you are at a pub, and you and your friend have had too much to drink. Your friend is really good at darts and says, "Well, I can shoot an apple off your head with a dart." And you're like, "I don't know. It doesn't sound like a really good idea to me." But how would you determine whether this is something you might even consider? Well, you might ask your friend, "Okay, try to shoot the bullseye on the dartboard, and let's see what kind of pattern you get. And if if I like the pattern, then maybe we'll go through with this game." I guess it depends on how much money you have riding on it too. Anyway, So here's our dartboard, and you instructed your friend to aim for the bullseye right in the middle, and your friend is doing his or her best to aim for the bullseye, and they get a pattern that looks something like this. Okay. So there's an obvious problem. They're missing the bullseye. Their average, the average is right about here, and it's way below the bullseye. And so that's the kind of problem or issue that a point estimator could identify. Right. And here is another kind of problem that can happen that the point estimator won't get. And that's that if your friend does this, in that case, their average is a bullseye. But they're all over the place. They're way on the outside. The point estimator won't detect that problem. The point estimator just says, "Oh, look at the sample, the sample mean, the average of all the shots. It's right on the nose. Looks like you're a winner here." But no, you're not. Your shots are still dispersed all over the place. And would you let a friend shoot an apple off your head who had that kind of pattern? No, I wouldn't think so. But the point estimator doesn't detect that. So what you really need is something that doesn't just detect the average, but also detects the spread. So here is the kind of pattern that you might like to see. So in this case, the average is the same in both cases. But the second one has a tighter spread. And we have a word for that. We have a concept. It's the variation or variability. Or also standard deviation. So this tells us how important the standard deviation is. Notice that in our point estimators, we haven't taken into account the standard deviation. So they're missing some valuable information that we could use. So we will do a lot with the standard deviation and what follows, and standard deviation will be an integral part of us finding interval estimators. So you see, interval estimation is, of course, much more complicated than point estimation. Point estimation is dead simple, and it's also highly misleading, and it's too simple. As Albert Einstein said, everything should be made as simple as possible, but no simpler. So the problem with the point estimator is it's too simple. It doesn't capture the variability. It doesn't allow us to talk with confidence about probabilities. And that's a lot of what we do in life is all about probabilities. So you're running a business, you're never going to be sure that your business is going to be a success, but you can be 95% sure, and that is pretty darn good. And so interval estimators will be connected intimately with all the stuff about probabilities that we've been talking about. So you see, we've been assembling all the information, all the ideas that we need gradually over this course, and so here we're finally in a position to use that information about normal distributions, about probabilities, and all this stuff. Now we can assemble it all into this very nice package and do some really interesting stuff with statistics with it. Okay, so there's a few more general concepts we want to talk about. Um, we have a few different types of estimators or properties of estimators that we're going to look at. So here, for example, is an x-axis, and our population mean is here. We may sometimes pretend we know what the population mean is, but later on we're going to drop that pretense. Sorry, and but for now we're gonna pretend we know where that population mean is. So that's mu. That's our population mean. Now, since the estimator is a process that involves taking a sample, the estimator will have a distribution. If you do the if you find a sample and make your do your estimator, and if I get a sample and do my estimator, we're going to get different numbers. So there's going to be a distribution of the different numbers. So what we hope for is a distribution that looks something like this. It's going to be pretty high around the actual population mean. So, if we do the experiment 100 times over, they're going to sort of, with high probability, cluster, the results we get are going to cluster around that population mean. What may happen instead is that we may get a distribution that looks like this. So as we do 1,000 people do experiments, the results are here, and the mean is not equal to mu. So it's not equal to mu. And this we call a biased estimator. So that's a problem. We don't want biased estimators. We want to avoid biased estimators. So mathematicians and statisticians have worked hard to determine when an estimator is biased and when an estimator is unbiased. You are not going to have to do all that work. It's very technical, mathematical work, but you should know the outcome of those investigations anyway. And I will tell you when an estimator is biased versus unbiased. And so all the useful estimators that we're going to use are unbiased. So we want an unbiased estimator. It's going to look like that one, the first one. All right, so that is one property of estimators that we're going to pay close attention to. Another one is, here's again, I'm going to put two estimators in. Here is one estimator for the mean, and here is another estimator for the mean. So this one is a narrow. This one is wide. And clearly the narrow estimator is going to be better, because if I do one experiment, I am, here I am about at least 68% likely to get within this narrow range of the actual mean. Whereas if you're using a wide estimator, then you're going to be, say, 68% or 95% or whatever we decide, likely to be in this much wider range. So having a wide standard deviation on our estimator is something we don't want. We're going to measure this quantitatively, and we're going to call this the standard error. So a standard error is very much like a standard deviation, but it's just that if we use the word standard deviation in too many different contexts for too many, if it has too many different particular meanings, it becomes confusing. So we introduce this new terminology, standard error. And so we want a small standard error. If we have an opportunity to design an experiment we want to design it so that the standard error is small as possible. And we're going to get into that kind of question very soon. So the kind of the prototypical way of communicating all of this is we have a population mean, we have an estimator, and for reasons that would become clear, the estimator is generally going to be a normal distribution. And as I've mentioned before, in the kinds of statements we make in science, we generally want to be 95% sure that we are, or we want to have 95% confidence. Let me put it that way. We want to be 95% confident that we are within a certain range of the actual value mu. So our sample may take us here, it may take us here, it may take us here, 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 here. 1 in 20 of our samples will be out of here. So but that's just the price that we have to pay in order to be able to do statistics. Is that we have to realize that we're wrong sometimes. 1 in 20 is an acceptable margin of error in science. Most of the time we're in here. When we communicate this, we're going to call this distance here, actually half of that from here to here, we're going to call this the margin of error. And that's the margin of error associated with 95% confidence. Now, we can change that confidence if we need to. And different disciplines sometimes do. So I was just reading about particle physics, and when they want to declare whether a new particle exists, you may have heard about the Higgs boson. So a lot of talk about, is the Higgs boson for real? Is it not for real? People have bets on, and it's going to change the future of physics one way or the other. In order to declare the Higgs boson real, physicists have decided they need to go 5 standard deviations out. Whereas in more normal science, you only need 95% confidence, and so that's 2 standard deviations. So that's the number that we will be using most of the time. 95% confidence is 2 standard deviations, roughly 2 standard deviations. If you check your table, you will see it's really 1.96. So it's approximately 2 standard deviations. It's more closely 1.96 standard deviations. That corresponds to 95% confidence. Sometimes we will change that number, so we'll have to learn how to change that number from 95 to 99 or some other number. Anyway, so that is just a little bit of vocabulary that we're going to use. This is the margin of error here. One more time is this distance here. The margin of error typically is actually about 1.96 standard deviations, very close to 2 standard deviations. Here is 1 standard deviation right here. And remember, we call this the SE. That is 1 standard deviation of the estimator. All right, so that is kind of our general discussion just to get you oriented. We will turn to specific calculations, which is really the most important part of this. The that completes our section, well, most of section 8.1, 8.2. We will finish off the rest very shortly.